Our today's tutorial is about problem 10.8, and in the problem it is given that the spring of problem 10.7 is to be used, which is forced by an amount of 16.5 lbf. We are required to do design assessment based on equation 10.13, 18, 19, 20 and 21 such that the spring is forced to solid height. So force applied is 16.5 lbf, and the data calculated from problem 10.7 is given as C is equal to 10 and A is equal to 7, SSY is equal to 101.8 kPSI. Solid force is 18.78 lbf, and the deflection in the spring when it is forced to solid height is represented by Ys, which is equal to 1.14 inches. Free length was 1.78 inches and critical length was 4.208 inches. All of this data is calculated in problem 10.7. I will provide you that video as well over here, which is 4 minutes and 14 seconds. So if you don't want to see the solution of problem 10.7, so skip this video by an amount of 4 minutes and 14 seconds, and then we will come back again to problem 10.8. This problem is about a helical compression spring, which is made up of hard drawn wire having wire diameter 0.08 inches and outer diameter of the spring is 0.88. The spring comprises of 8 coils. We are required to find out the free length, and then we will have to find out the pitch of the spring. Then in part C we are required to find out the solid force, and D we are required to find out the spring rate K, and lastly we will have to find out whether buckling would occur or not, as the ultimate tensile strength is equal to L divided by D to the power m, and m values are taken from table 10.4, and in the table for hard drawn wire m is equal to 0.19 and A is equal to 140 kPSI. Putting these values in the formula, that will yield 226.2 kPSI, as torsional yield strength is equal to some percentage of SUT, and that percentage is taken from table 10.6, which is 45% for music and cold drawn carbon steel. So SSY is equal to 0.45 and 226.2, that will give you 101.8 kPSI. Now from table 10.1, NT is equal to Na plus 1 and free length is equal to P into Na plus 1 and pitch is equal to L naught divided by Na. So from the table, Nt is equal to Na plus 1, rearranging for Na, that will give you Nt minus 1, Nt is Z, so Na is equal to 7. Similarly, Ls is equal to dNt, d is 0.08 and Nt is Z, so Ls is equal to 0.64 inches. This 0.88 is external diameter, so mean coil diameter is equal to external diameter minus wire diameter, which is equal to 0.88 minus 0.08, which will give you 0.8. So mean coil diameter is 0.8 inches, and C is the ratio between mean coil diameter and the wire diameter, so 0.8 divided by 0.08, that will give you 10. So C is equal to 10. Now KB is equal to 4C plus 2 divided by 4C minus 3. C is equal to 10. So KB is equal to 42 divided by 37. That will give you 1.135 cube. S is equal to KB into 8F D divided by pi D cube. This D cube is wire diameter cube. So now replace ta with ta s and F with Fs. Factor of safety is equal to torsional yield strength divided by tau s. So tau s is equal to SSY divided by factor of safety. So SSY divided by NS is equal to KB into 8Fs D divided by pi D cube. Now rearrange this equation for Fs. So Fs is equal to pi D cube into SSY divided by NS whole divided by 8 into D KB. In this equation, all other values are known except this NS. In the book, it is given that factor of safety should be at least 1.2. So for safe operation, we will take NS equals to 1.2. So put the lowercase d to be 0.08 and SSY is equal to 1.101.8 and to 10 is to power 3, and NS is equal to 1.2 and KB is equal to 1.135 and mean coil diameter is equal to 0.8. So put all these values, that will give you Fs is equal to 18.78. Now let's find out the value of the K so that we can find out Ls. Then from the equation F is equal to Kx and L naught will be equal to Fs divided by K plus Ls. So for the K, we need to have value of the G, which can be found out from the table, and D is equal to 0.08 inches. This is 0.8 and N is 7. For hard drawn spring, our diameter is between this range, which is 0.08. So the G value for it will be 11.5. So putting the values, that will give you K is equal to 16.43 lbf per inch. So L naught is equal to 18.7 divided by 16.43 plus 0.64, and that will give you L naught is equal to 1.78 inches. This step is not needed if you do it directly like this. Now we are required to find out the pitch. So using table 10.1, pitch is equal to L naught divided by Na plus 1, and if you see Na plus 1 is equal to Nt, so pitch is equal to L naught divided by Nt. L naught is 1.78 and Nt is 8, so 1.78 divided by 8 will give you P is equal to 0.223. And part C, we were required to find out solid force Fs, and we have done that part already. Fs is equal to 18.78 lbf. And in part D, we were required to find out the spring rate K. We have calculated or found out that as well. So K is equal to 16.43 lbf per inch. In part E, we were required to find out whether the buckling would occur or not. So to avoid the buckling, L0 should be less than L critical, and L critical is equal to 2.63 into mean coil diameter divided by alpha. Alpha value can be taken from table 10.2, and when the spring is supported between two parallel flat plates, then alpha is 0.5 and D is 0.8, so 2.63 into 0.8 divided by 0.5, so L critical is equal to 4.21 inches, and this value is greater than L0, which was 1.78, so buckling will not occur. Coming back to the problem 10.8, so all of this data is taken from problem 10.7. Now what we will have to do is to check all of this data based on equation 10.13, 10.18, 10.19, 10.20 and 10.21, and these are those equations. This is 10.18, this is 19, this is 20, and this is 10.21. So let's take this equation and see the value of C, whether it is in the range or not. Since C is 10, which is greater than 4 and less than 12, so we are in the range. So based on this equation, our design is okay. Now let's take this equation and see the number of active coils exist within the range or outside the range. So as n is equal to 7, so we are in the range and the design is okay up till now. And in the next equation, it is given that the zeta value should be greater than or equal to 0.15. And since zeta value is not given over here, so let's find out the value of the zeta. And previously, from 2 to 3 problems from chapter 10, we have told you that zeta into F plus F is equal to Fs, where Fs is solid force. So from that equation, we can find out the value of the zeta. So zeta is equal to Fs divided by F minus 1, as Fs is equal to 18.78 lbf, F is 16.5 lbf. So putting these values, zeta will be equal to 0.14. Since the value of the zeta is less than 0.15, so the design is not perfectly okay for us, but we can still go with this design because 0.14 is not very much smaller than 0.15. Now let's find out the factor of safety, and it is equal to torsional yield strength divided by the shear stresses produced due to the applied load, so that is tau 1, and SSY is given to us, so let's find out tau 1, and tau is equal to kb into 8fd divided by pi d cube, and this kb was calculated in problem 10.7 from the equation for C plus 2 divided by for C minus 2, and it was 1.135. This F is 16.5 and this D is, it was 0.8 inches, and this D was 0.08 inches. So by putting all these values, it will give you tau 1 is equal to 74.5 kpsi. So factor of safety is equal to SSY divided by tau 1, and SSY is equal to 101.8 kpsi, and tau 1 is equal to 74.5 kpsi. So factor of safety is equal to 1.37. As factor of safety should be equal to or greater than 1.2, and in our case it is 1.35, so the design is okay up till now. Now let's find out the shear stresses produced in the spring when solid force is applied. So for that, let's take the ratio of tau s and tau 1. So that will be equal to Fs by A divided by F1 by A. A will be cancelled out with each other, so tau s divided by tau 1 is equal to Fs divided by F1. Now multiply tau 1 on both sides, so tau s is equal to Fs divided by F1 into tau 1. Fs is 18.78 lbf and F1 is equal to 16.5 lbf, and tau 1 is equal to 74.5 kpsi. So putting all these values, tau s will be equal to 84.8 kpsi. Now let's find out the factor of safety based on the stresses produced in solid spring. So factor of safety is equal to torsional yield strength SSY divided by tau s. SSY is 101.8 kpsi and tau s is 84.8 kpsi. So factor of safety, or in S, will be equal to, it is equal to 1.2. So as factor of safety should be equal or greater than 1.2, so our design up till now is okay. So if you force the spring to solid height, then the spring will still be safe from failure. And if you see, this is the L0 and this is the L critical. As L0 is less than L critical, so buckling would not occur. So the design is okay for us, and we can use this spring in many applications. Thanks for watching the lecture. We will continue our lectures on the spring, so if you want to get more updates about the spring, so subscribe to our channel and keep watching the lectures.